All right, this question reads, define gravitational field strength. So gravitational field strength really tells us how many newtons of force act on each unit mass. There's two ways we sort of think about gravitational field strength. There's the acceleration due to gravity. So on Earth, we know this is 9.8 meters per second per second. So it's telling us this is how much velocity something picks up every second. Every 1 second something falls in Earth's gravity, it picks up 9.8 meters per second of velocity. And so we say the acceleration due to gravity is 9.8 meters per second squared. That's one way to sort of think about the gravitational field strength, how quickly the gravity field accelerates things. On Jupiter, this number is 23 meters per second squared. So things actually gain 23 meters per second of velocity every second they fall. The other way to think about that is how many newtons of force act on each kilogram of matter. So as I sit here in my chair with 100 kilograms of mass that I possess, there's 9.8 newtons of force pulling down on each kilogram. So my weight is 980 newtons. So the force due to gravity is your weight. And in newtons, it's just, mass times the gravitational field strength. So the gravitational field strength, if we kind of use this definition, tells us the amount of force acting per unit mass. Force per unit mass, right? So that's the force acting on unit mass tells us the strength of the field. On Earth, the gravitational field strength is 9.8 newtons per kilogram. On Jupiter, it's 23, newtons per kilogram. It says the mass of a spherical comet of radius 3.6 kilometers is approximately this. Assuming that the comet has constant density, calculate the gravitational field strength on the surface of the comet. So we've done this before with Earth, where we've calculated this gravitational field strength by taking Newton's second law, F equals ma, and setting it equal to Newton's law of universal gravitation, gmm over r squared. So we just solved for the acceleration due to gravity as the gravitational constant g times the mass of the planet, or comet in this case, divided by its radius squared. So we sort of assume that all of the mass of the comet exists at its center, the radius sort of away from its surface. And that's the distance between sort of, here's some mass on the surface of this comet, but again, we sort of approximate all of the 1.0 by 10 to the 13 kilograms exists right here, sort of separated by this distance r. So all we need to do to calculate the gravity field strength is substitute into this equation g, the mass, and then r squared, it tells us the radius is 3.6 kilos, so 10 to the 3 meters squared. So that calculation there will give you how strong gravity is on a comet, 6.67 by 10 to the negative 11th times 1 by 10 to the 13 divided by 3,600 squared, 5.15 by 10 to the negative 5 meters per second squared, or newtons per kilogram. So it's a very, very weak gravity field because it's a comet and not a planet, right? So if we were to sort of land on a comet, that's the kind of gravity fields that we'd be dealing with if it were these dimensions. Landing on a comet. It says a probe having a weight of 960 newtons on Earth lands on the comet. Using your answer, determine the weight of the probe on the surface of the comet. So keep in mind that value 5.15 by 10 to the negative 5. That's how many newtons per kilogram of gravity field strength there is on the comet. So on Earth, it weighs this. Weight is the force of gravity equals mass times the acceleration due to gravity. If on Earth, something weighs 960 newtons, we can calculate its mass by dividing each side by g, right? So 9.81 newtons per kilogram. So those newtons cancel, we're in kilograms of mass. And we know that 960 divided by 9.81 is 97.9. 97.9 kilograms of mass. Okay. Now we want the weight of the probe on the comet. So the mass of the probe doesn't matter where you are in the universe. That's how many kilograms of matter. The weight is the influence of gravity on that mass. And so the 97.9 kilograms of matter anywhere in the universe happens to be on this comet now, 5.15 by 10 to the negative 5 newtons per kilogram. So we use the data for Earth to figure out its mass, and then we just know mass is the same everywhere. So mass times this g times 5.15 by 10 to the negative 5 gives us a weight of 5 by 10 to the negative 3. 5 by 10 to the negative 3 newtons, so 0.005 newtons. It hardly weighs anything. On Earth, it weighs 960 newtons. Okay, so this is close to my mass. Remember, I said I'm 100 kilograms. So I weigh about 220 pounds. And so something that weighs 220 pounds on Earth weighs basically nothing on this comet. It has a weight, but it's very, very small. The question goes on to have you consider a second comet that has a length of 4.5 kilometers and a width of 2.6 kilometers. And it says, suggest one similarity and one difference between the gravity fields at the surface of this comet and at the surface of the comet in B. So we actually landed a probe on a comet that kind of looked like this several years ago. The name of the lander was the Philae lander. It was not the OSIRIS-REx, it was the Rosetta spacecraft. So the Rosetta spacecraft, it was sort of orbiting around this, and it dropped down a lander and studied it. That happened a few years ago. And so these dimensions will probably give this thing roughly kind of the same. I mean, remember that the one that we just had was a sphere that was 3.6. So this one's a little bit longer this way, but a little bit shorter sort of in its width than the 3.6. And so you probably find that like the average gravity field is about the same. In other words, they have similar gravities, provided they're the same densities. Like this could be made of a completely different, sort of material, but it's a comet, and most comets are sort of all the same. They're just like dirty snowballs, basically. That's when they get close to the sun, they get vaporized, and we see their sort of ion trails. So a similarity might be that they have roughly the same field strength, but a difference would be it's not going to be uniform. So everywhere on the surface of the sphere, you're the same distance away from, like, remember, we're assuming all the mass is here. So that point is the same from that point is the same from that. Like all these radii are at the same distance. Here, it's like, well, the gravity here might be a lot stronger than the gravity out here, right? Like these distances are obviously different. They sort of tell us that. So it wouldn't be a uniform field, like a strong field here and sort of a weaker field up here. Whereas all around this, the gravity field is exactly the same, denoted by the length of this vector. So a similarity would be, kind of about the same strength, but different on different places sort of around it due to its shape. All right.